Yeah, good evening, everyone. So, we are pleased to have Dr. Maruk Khan with us. And I would like to share with you that our chapter has won MTT Best Student Chapter Award in 2021, Darren Chong Student Activity Award in 2021, and APS Best Student Chapter Award in 2022. It has also gotten a side project that we have successfully completed this year, and we are looking forward to many such events and activities. And I would like to ask Dr. Vivek Dixit sir, our faculty advisor, to introduce you to the audience. Kindly, sir, please take over. Sir, you are muted.
Okay. So thank you, Shreya. Okay. Welcome, Dr. Maruk Khan. It's our pleasure to host you today, and thank you for agreeing to deliver a talk. Pallav, send me your bio. So Dr. Maruk Khan is working as an assistant professor in the Electrical and Computer Engineering Department at the College of New Jersey. So she received her Bachelor of Science and Master of Science in Electrical Engineering from the University of Engineering and Technology, Lahore, Pakistan in 2007 and 11. And Dr. Khan received her PhD in Electrical Engineering from the University of Missouri, Kansas City, Missouri, USA in 2017. And later she works as a postdoc fellow in Nano and Microelectronics Lab at UMKC. And then in early 2020, she joined as assistant research professor at the Missouri Institute of Defense and Energy. And she has published more than 20 articles and conference papers in renowned journals and peer-reviewed conferences in her field of research. Her research articles and conference paper have received more than 200 plus citations in a short period. She has won an honorable mention in the International 2015 Altair FACO Student Competition. For your information, FACO is a software company, so that makes a software for electromagnetic simulation. And she has also won the prestigious UMKC School of Graduate Studies Fellowship for her outstanding research. She got the UMKC Women Council Fellowship Award in 2015 and 16. And in 2016, she was also selected for the UMKC Outstanding Graduate Student Award at the CSEE department. So recently she has been chosen as a 2022 IEEE APS Young Professional Ambassador. She is a reviewer of top journals such as IEEE Antenna and Propagation Magazine, IIT Microwave Antennas Propagation. And Dr. Khan is an active member of IEEE Young Professionals and IEEE Women in Engineering. So let us welcome Dr. Maruk Khan. And thank you very much again. Thank you again for agreeing to give a talk. Thank you.
Thank you, Vivek, for introducing me. I will start the talk. Just a second. Yes. So you can see my screen now, right?
Yes.
Okay, because I cannot see you guys, so just like, yeah. So thank you, Vivek, for introducing me. Today, the topic of the talk is miniaturized ultra-wideband antennas for IoT and wearable applications. As Vivek mentioned, I'm an assistant professor at the College of New Jersey in the Electrical and Computer Engineering Department. And I'm also 2022 IEEE APS Young Professional Ambassador. This is a little bit about me. Vivek already introduced me, so yeah, I think it's just that I have done my PhD from UMKC, and I'm also working as the assistant professor at the College of New Jersey. Before that, I have this experience of postdoc and assistant research professor. These are some of my selected publications in journals. So the paper that I have published in this special issue of IEEE TAP received more than 100 citations. So this is some of the record. I also received the NSF Engineering Research Initiation Grant of $200,000 this year. And I'm also selected as IEEE APS Young Professional Ambassador this year. So my research interests are mainly focused on ultra-wideband antennas, characteristic modes, 5G MIMO antennas, and satellite communications. So before starting my talk, I want to talk about a little bit of IEEE APS Young Professional Ambassador Program. I think this is a very good program for those who just graduated or in this field, in the professional field of antennas and propagation, and they want themselves to be recognized, or they want to collaborate. So you need to have 5 years experience in this profession. You need to be IEEE member and Young Professional member too. So this is the first badge of IEEE APS Young Professional Ambassador, and in this badge there are 12 members. I am among the 12 members. So we actually are giving the talk until now. I think it's been more than half a year, and it's a great experience. I learned a lot from this experience and this program. We arranged several events in the APS, and we got to meet some great professors, and we had some personal interactions with them. So I think it's a great program. So I will encourage everyone to apply this next year. So coming back to my talk, we all know that future of wireless communications, antennas is very fast and furious. Everything is becoming high speed, really fast. So we need to be keeping our pace up to that level. So this is just an example of this. So this is a Pope election in 2005, and this is the Pope election in 2013. What a huge difference we made, and what a progress we made in this wireless communication in just 8 years. So it's booming, and it's coming and coming. So we need to be really keeping up with the pace. So what is IoT? I heard about IoT so many places, but what is IoT actually? Well, IoT is actually the network of the sensors, softwares, and other technologies that can be connected through internet. So they could be anything. They could be smart devices in your home. They are some communication hardware that can collect and process the data. And IoT devices can communicate with each other without human. So that like the concept of IoT bring a lot of change in our daily environment, and it's a huge thing. So with more than 7 billion connected IoT devices today, experts are expecting that this number to grow to 10 billion by 2020 and 22 billion by 2025. So it's a huge thing. I mean, it's like that you have connections everywhere in your home, in your offices, in your industries. So IoT is bringing the revolution. I think it's already here, and future will be more about IoT, I think. So these are some application domains of IoT. If we see, we know that it's everywhere. You think of it, and IoT would be there. So our smart home, smart transport systems, smart cities, healthcare, industrial automation, and agriculture, it's everywhere. So these are some of the examples of the application domains of IoT. If you think about IoT framework of home automation, we know that this would be the framework where cell phones, light systems, smart appliances, security systems, TV and home theater system, other integrated systems or car security would be interconnected and would be having server to process the data so that they can be easily connected to them. So it has huge advantages for those who live alone, who are elders, and others like who are concerned with their security without without, putting too much effort. So normally, we know that our Wi-Fi works at 2.4. So these are the devices that work at 2.4 gigahertz and 5.8 gigahertz as well. So there would be a connected system for the home automation. So this is an example of one of the IoT framework for the home automation. And we know that as these devices are wirelessly connected, so we, of course, for any wireless connection, we need antenna. So what is, as we are all associated with antennas and propagation, so we will be knowing, or we will be concerned about what would be the requirements of IoT antennas. So there are some basic requirements of IoT antennas, then there are sub requirements. So one of the basic requirements is that they should be compact, because they will be everywhere. They will be connected to smallest device you have in your home, and they should be compact and small. The other thing is they should have less energy consumption. Like if they are connected to some device, they should not consume so much of energy of that whole device that the processing and other things are becoming difficult. So they should consume less energy. The third is that they should have the ability to work in multi-antenna environment. Like if there are other antennas present, they should be less prone to interference. Similarly, they should have good ability to communicate without interfering other systems. So they should have some pattern reconfigurable, something that they should be able to perform in other multi-antenna environment. They should have less interference. So compact means that they should be miniaturized, right? So because we know that normally the antennas that we make, if they are microstrip antennas, they have certain frequency, like they work on lambda by 2, like the size, and but we should find the ways to miniaturize them because we want to fit them in the small devices. Then they should be easily integratable to the system they are connected to. So they should have an easy integration. Another thing is most of the IoT antennas are narrowband, because when you miniaturize them, it's hard to keep their bandwidth. We will talk about it in the next slides, that what is how they can be narrowband and ultra wideband. And then less energy consumption means if they have the less energy consumption, they will be having a low cost, because they will not have big requirements of energy. Like they should be having a great battery life as well. So they should be pattern configurable, reconfigurable, that they should be able to switch their patterns. It's not right like the hard requirement, but that's a good way that if they will be able to switch the beams, that is great. Even if they are able to perform in the presence of other antennas, that's also great. And they should be preferably directional, so that we consume less radiation power because of that. So these are just some of the requirements of IoT antennas that we think of when we try to build them. So whenever we design antennas, we think about what are the hard requirements, and then if we get the plus of them, that's a good thing. But if we are getting the plus requirements and we are not meeting the basic requirements, then it's not of no use. So that's what we think as an antenna designers. Another thing is in US, the operating band is 915 megahertz. And for IoT devices in Europe, it's 868 megahertz. This band is chosen because of the reliable propagation characteristic. But as I have mentioned, for the home automation, normally they work at 2.4 gigahertz, which is also fine. So there are different bands that exist for IoT devices. Okay. So when we talk about miniaturized antenna, what is miniaturization? I think miniaturization is the process in which you try to reduce antenna size than its original size. So that is the requirement. I think that is the basic requirement for IoT, that they should be miniaturized than their actual size. Because if you are working at 915 megahertz, your antenna would be big, but you have to find the ways to miniaturize that antenna. So why we need miniaturization? Because miniaturization with the miniaturization, we will have we will able to use the less space in already congested systems, and there will be miniaturized antennas that can be easily integrated in the circuit. Now you know that your mobile phone has so many antennas in it, so it is already congested. So if you add one more antenna, it cannot be added in any device if it is not compact. So that was the main requirement for IoT. So we know that there are several miniaturization techniques that we adapt. So some of them are structural folding. That is one of the technique for IoT. Then there is slots and slit incorporation. That is another technique that we use to miniaturize IoT antennas. Then there is resistive loading. Material loading, like metal surfaces or defective ground structures that we use to do the miniaturization. Then there is meander line that we use to do the miniaturization. So these are some of the famous miniaturization techniques that people used to build IoT antennas for the miniaturization. So if I go further, so this is one of the antenna that achieved 95% miniaturization, which is huge. What they have done is they did this structural folding. It's a little bit, I think, complex in the term that you can see that they have this 2D system in which they have the slits, and they try to structurally fold this antenna 3D and made this 3D antenna. So it's a 3D antenna. It's not like what you should say, the planar antenna, but the miniaturization they got is huge. Like this 95% miniaturization. If you see that it's comparable with the coin, and it's operating at actually 800 megahertz. And with this operating frequency, this kind of the antenna is a huge success, I feel. It's the another thing is that it's a directional antenna. So with the miniaturization and at this low frequency, you lose a lot of radiation efficiency. But as IoT antennas work in the environment where all the other antennas are near, so you can bear that much of the radiation efficiency. So that is one of the antenna that I really like, that because they got a very good miniaturization. Then there is a miniaturized ZigBee antennas for IoT. That antenna, that was the main antenna, like the monopole antenna. They were able to reduce it to using the meander line. And at this antenna, they got the 50% miniaturization. The resonant frequency was 915 megahertz. This antenna was the omnidirectional antenna. And you can see one of the return losses for the monopole and one of the return losses for this meander line antenna. With the meander line, you can also achieve a big, what you should say, miniaturization. So that's one of the antenna. And in this paper, they also showed it, I think, connected with the device. So I think this is another good way of miniaturization in which you can introduce a like the meander line and try to miniaturize that antenna. Another miniaturization, good miniaturization technique. So in this antenna, you can see that they were able to get the huge miniaturization by what you should say, by evolving this antenna. So this was the first version of this antenna, and they just keep adding slots and slits by looking at the currents. So that was the first version, second version, third version. They can get the miniaturization. They start getting the miniaturization from 7 gigahertz till this, and then they add further like the loading. That's what we call the loading, when you add the some kind of the slot. It's not a slot, but some kind of the what you should say conductor. So they also get miniaturization evolving from antenna 1 to antenna 5, which is also good. And this antenna works at 2 bands, as you can see, the red line. It can work at the C band and for 5G Wi-Fi. And the size of the antenna you can see is like the SD card. So that's also good for this antenna. And these are its radiation patterns of the antenna. So this is also another example of miniaturization using slots and slits. So this is antenna the got from a defective ground structure. And this is a frequency reconfigurable antenna. That's interesting. because in this antenna, what they did is they have these capacitors, and with this, the help of capacitors and with the help of this, I think, voltage line, they were able to get this miniaturization, and they were able to get this frequency reconfigurable miniaturization with the different voltages you can see here. And with every frequency that it is operating on, they were able to get this different peak gain, and it was a directional antenna. So with the IoT antennas, if you get the directional, some of them are omnidirectional, some of them have very low radiation efficiency because of the degree of miniaturization you got. So if you get the directional pattern, that's a huge thing. So I think they got good gain for different frequencies, more than 0 dB, and good radiation efficiency as well with DGS. So that is another one of the antenna they got for the miniaturization. With our research group, we also doing miniaturization for IoT, and we also got some good miniaturization by adding slots in the antenna, and we are in the process of publishing it. But we also got some good results at, I think we are doing at 2.4 gigahertz. So that was about IoT antennas. So now we will go towards the wearable antennas. So we know that wearable antennas also cover a large domain. They are in security and safety, they are in medical, wellness, sport, fitness, lifestyle, computing, communication, glamour, everywhere. So talking about wearable antenna, we are coming in a different domain than like IoT antennas. So what is, like, IoT and wearable antennas are same? No and yes. Because wearable antennas can be part of IoT, but there is more important factor to consider in wearable antennas, because when you come towards the IoT antennas, you are not thinking about the antennas that will be on the body. But with wearable antennas, there is another factor that comes into place, because IoT antennas are on the devices, which are not a living thing. So in wearable antennas, you need to be very, very concerned about specific absorption rate, because that's a human or living thing that is involved now. Another thing that is considered in wearable antennas are bending issues in conformal antennas, because when you wear the antennas, there will be some bending, and so that should be also considered in case of wearable antennas. So this is one of the wireless body area network. So you can see in this network how it operates. There is in wearable antennas, there are some like on-body and off-body antennas. So if you can see that you can have a motion sensor, you can have antennas that can get your heart rate, BP, ECG, EEG, and they all should be able to send the signal, make a link with the control unit or the mobile devices that can be sent to the internet. So they are part of IoT, but they are also, we also need to consider other type of things in the wearable antennas. So going further, I really like this paper in which they were talking about, they were suggesting that how you choose the whole body area network to be considered. So if you see in this antenna, that is antenna that is on body and able to maintain on body link and off body link. So this is kind of the pattern reconfigurable antenna. In this antenna, they were able to make the links and steer the beam as well. So with this switching, and they were able to make the in-body and off-body link with this antenna. Then there is a hip implant antenna that is also reconfigurable repeater antenna. So this antenna, because it's an implant, this is built on the magnetic, what you should say, material, because magnetic material has the less, what you should say, the absorption in the body. So that's why this antenna hip implant was that was able to do the in-body and off-body connection. So this is a kind of the antenna that is implant antenna. Then there is an antenna that is used as the watch, can be used as a watch, and this antenna is also reconfigurable, but the property of this antenna, why it was chosen for the the watch or for the hand, because it is a dynamic antenna. Dynamic antenna means that it is able to make the connection when there are a lot of changes happening, and because your hand moves all the time. So this antenna is able to make a reliable connection with the body. So that's another form of the antenna, that is reconfigurable antenna. So these are different types of antenna that are chosen to be making a wireless body area network. And in this paper, they're talking about how you choose the antenna, wearable antenna, to make the body area network. So what are the considerations you should make? So this is a really good example of making a body area network using wearable antennas. Then there is another wearable antenna. So now the difference here, you can see that wearable antennas should be wideband, ultra wideband. And this is one of the antenna that is made. So you can see there are some slits. And they made it first on FR4 for the proof of concept, and then they converted to the genes, like the material, to make it. And they showed here that this antenna on FR4 has such a wide bandwidth, and then on genes, it is able to maintain that wide bandwidth. So that's a great example of showing that how the change in material can be optimized to give you the very wide band antenna. You know that for wearable antennas, you need the wide bandwidth because you need to process more data. You need to have the high speed as well. And in this antenna, you can see that bandwidth is almost maintained as in the genes, and as well as gain is also not bad now when we have the genes material thinking about FR4 as it is. So this is also another form of miniaturized antenna for wearable applications. Okay, so I talked about first that what is the most important consideration, which is not a consideration in IoT mostly, that is the consideration for wearable antennas, is the specific absorption rate. So we need to have the specific absorption rate that is less than 2 watt per kilogram as in US standard. So if you see that what is specific absorption rate, it's actually that because of the high conductive material in the human body, when we place antenna near the human body, we get detuned due to a mismatch in impedance and some portion of the available power absorbed in the body, which if it is consumed more than this standard, it will be harmful for the human body. So we want to make an antenna that is have the specific absorption rate that is less than this quantity. So this is a very good example of showing that how you can reduce specific absorption rate of the wearable antenna if you want to make it wearable. So what they did is, this is one of the patch antenna, which has a good absorption rate, but it was not near the human body in this case. But now when they made it on human arm, you can see that the specific absorption rate increased hugely because here they didn't check any proximity, but here they checked the proximity. So the specific absorption rate increased too much. So what they did is they introduced a high impedance metamaterial surface in this antenna, and they were able to reduce specific absorption rate after this. And then they added a VS, and they were further able to reduce the specific absorption rate from 2.36 to 1.77. So this is a great example how you can make your antenna wearable by making changes in the antenna, or by introducing high impedance metamaterial surface that is able to reduce the adverse effect of the backward radiation. So that's a great, I think, antenna for wearable. And for all wearable antennas, whenever we make them, we should be assessing the SAR level as well, because that's the basic requirement for the wearable antennas. So first, I will discuss some challenges and limitations of the IoT antennas. For IoT antennas, as I described before, that antenna efficiency is a big challenge because we are miniaturizing the antenna. You cannot limitlessly miniaturize antenna without thinking about antenna efficiency. Most of the IoT antennas have limited radiation efficiency. And when you design them, you cannot just keep miniaturizing it. You need to know for what application you are designing so that your radiation efficiency should be in the limits. Secondly, because there is a limited energy available for IoT devices, so to reduce the overall energy consumption of the entire IoT network, we should take into account this effect as well, that we have the limited energy available, so these antennas should consume less energy. This is very important issue that they have. Most of the miniaturized antennas, they have increased sensitivity towards the environment, and whenever they are introduced in front of other antennas, their performance changes a lot. So this is another form of antenna limitation that we have. So possible solutions could be that the IoT devices component which are close to the antenna. So whenever you design antenna and you know that this could be the potential limitation, you need to include that into your simulations. So that could be included in the simulation to know that this could be optimized as in like the circuits and batteries which are in the close proximity. Then most of the IoT antennas, you saw some like kind of radome or some protective device that isolates the antenna from the closest environment. So that's another form. And similarly, there are some more complex solutions to produce some antennas, which I saw when I was doing the literature side. I saw some very, very complex antennas that can have the reconfigurable capabilities for IoT. Okay, and some limitations of wearable antennas. So we need flexible or small size rigid antennas that sensor can be incorporated seamlessly into clothing or body. So because it's not easy that you made an antenna or an effort for it, you can just not shift it to the jeans or any clothes or the surface that can be bended. So it's limitations that, but when you make an antenna, it should be able to be wearable. Then if you introduce it a near lossy surface, its frequency response changes and radiation efficiency degrades. So your antenna should be able to operate there. Then there is an FCC limit for partial body exposure that should be taken into account. Then if your wearable antenna is intended for more than one type of the link, or if it has to perform on body and off body both, it should meet both of the requirements as well. So that's another thing that should be considered. So one of the thing is that if you are able to decrease the number of retransmissions of making the link, by having higher antenna gain or pattern diversity, then you can save some of the battery life with the wearable antenna. Because you know that if you have this Garmin watch and there are some mountaineers that are going on the mountains, they need to connect with the internet and they need to save their battery life. So we need, as an antenna designer, we need to consider that whatever antenna we make should have large battery life and should be able to perform in the adverse environments. So conformity and body phantom should be included in the design process, and the antenna should be electromagnetically isolated from the human body as much as possible with the ground plane. So, which means that whenever we design antenna, it's always, if I see a wearable antenna, I always search the description of SAR. Like, what is its SAR level? I all the time search in the paper, did they describe their SAR level or not? Because it's very, very important for the wearable antennas. Thank you. If you have any questions.
Yeah, thank you, ma'am, for such a wonderful session. I would request the audience to unmute themselves if they have some question and to ask the question directly to Professor Marooq Khan. I cannot see any question in the text here. So if you have any question, kindly ask her.
Yes, Dr. Khan. So I have a small query actually.
Yeah.
So yeah, so I was checking this paper like S Dimoni on body antenna. So could you like go to the slide on body antenna? So like
oh, 1 second.
So like on body antenna link means, is it like that it will be going directly, because they are telling about secured communication on body most of the time?
Yes, which one?
Yeah, on paper on S Dimoni on body slide number. Paper on, yeah, exactly. So this on body link, yeah. So is it like a secure thing, like kind of like, because antenna will be radiating in all directions, right? So like it is from body, like from hand from right hand to the left hand. So like how is this communication being done? Like it will be because it will be radiating like antenna in all direction, means a person will be nearby, he also will be having information about the person.
So which antenna exactly you're talking about?
On the hand, exactly. Antenna
that's what they are talking in this paper, that it should be operating in the dynamic channels, right? That let's say if you have this antenna that is steering at one direction, and it should be able to steer at the other direction too. So it should be operating in the dynamic channels without interfering other antennas. So that's one of the requirement if you have the antenna for a smartwatch. Yes.
Okay, fine. And the other small query is like, why exactly like wearable antenna needs high bandwidth? So is it only because of transfer, or there are other reasons?
Yes, because they need to be replying quickly, right? They are high speed data that you need to communicate. Otherwise, there is another thing is that they should be sometimes they operate in the time domain applications, and in the time domain application you need to send them a really thin pulse, and that was like the needed for the imaging applications. So normally wearable antennas, we want them to be the wideband antennas because of the information we share with them. Because with the IoT antenna, it's just a signal that you send, right? But for wearable antennas, there is some data that you need to get from the body.
Yeah, and it's really like new thing that we knew about this sending pulse. So this final question is regarding because it said like you cannot achieve anything. So once you have the miniaturization, so what we lose actually?
We lose radiation efficiency. So once you miniaturize the antenna, it's very hard to miniaturize ultra wideband antenna and keeping the radiation pattern as well. And it's hard to miniaturize antenna with keeping the radiation efficiency. As you can see that most of the miniaturized antennas have the radiation efficiency in 50%. So most of the miniaturized antennas for IoT cannot perform for a long distance. So that's why there are some limitations that if you have a miniaturized antenna and you have in this environment, the network devices should be near to each other because they will not be having a large radiation efficiency.
Thank you very much. Actually, it's really a nice session. So, any other questions?
Hi, Dr. Khan. This is Arup. Hi. So it was a nice talk. I just want clarification towards the beginning of your talk in one of the slides where you're speaking about the requirements of an IoT antenna. You mentioned that it must not consume power, something like that. So I was just wondering, since antennas are basically passive structures, what do you mean by this? Yes, less energy consumption. So what exactly do you mean by this?
So what I meant is that when you have this antenna, you need a transmit power, right? Like it should have a gain when you have an antenna. So what I mean that it should have enough gain that it should reach the point that it has.
I understand. So actually you mean to say that there should be less dissipation of that.
Yes, less dissipation, because otherwise your SNR will be very low.
But that is actually most challenging for a designer, because since it is commercial, you would be going for this commercial PCBs probably. So it is really one of the challenging tasks.
Right, it is. And another thing is that when you make an antenna, once I was making an antenna for satellite, and we were thinking that more structure you have on the, what you should say, the substrate, more radiation efficiency you lose. So it's also should be very small. So that's why.
Yes, so it goes on the directivity also. So it's really challenging. Okay, thank you. I have listened to you before also during the WAMS recently and once in APS. So it's good listening to you again.
Thank you. Thank you very much.
So, to be Dr. Arup Ray actually. So he just completing his PhD, and he was also the past chair of AP-MTTS actually. One of the founding chairs, I would say actually.
Okay.
So thank you, Arupda, once again.
Thank you very much.
Thank you. So there are any other questions, I guess. Yeah. So there are really good comments. So actually, we had more than 50 participants.
Yeah, I'm seeing it.
More than 50 participations actually. Nowadays, actually, online talks are becoming so much saturated. It's very difficult to find participants.
Yes.
But it's still we used to capture. Thank you very much.
Yeah, I tried to keep it less complicated and more of the way that it reaches everybody. So yeah, it's good, I think. Thank you.
Thank you very much. So Shreya, you can final.
Thank you, Professor, for joining us. And thank you, everyone, for attending this wonderful session. And thank you, everyone. I mean, this was a wonderful session.
Thank you.
Thank you. Bye.
Good day. Good night, guys.
Good night. Yeah. So hope to meet you in physical sometime.
Yeah, so soon. Yeah. Thank you. Bye.
Bye now.